Hey guys, my name is Sandeep Patel. I'm the founder of Slowify.ca. In this video, we're going to learn about time complexity in very depth. I see a lot of people, they explain time complexity in a very complex manner, but in this video, I'm going to be trying to explain this in a really easy manner so that you can understand what it is and how to calculate. Alright, so let's begin our video. So let's start with the simple explanation, right? So computers, they're limited in terms of what they can do, right? So the modern computers, the CPU can execute 10 raised to 8 operation per second, right? And that depends on the different computers, right? If an algorithm exceeds this limit, which is usually 1 to 2 seconds in the context, um, then you get the TLE error, right? Time limit exceeded error, right? Um, So in terms of time, the computer is limited on how many operations it can execute per second. And that is the reason why we want to calculate time complexity of our program so that we don't exceed this limit and do not get the time limit exceeded error, right? Just imagine that you're running a big scalable software, right? And then you have like 1,000 or maybe 100,000 line of code, and if you, let's say, if there's a piece of code that takes a really, like it's written really bad way, such that it takes a lot of time to execute, in that case the time limit will exceed and your server will start doing 502 errors, right? Because your code is not optimized enough, right? So the idea is that using time complexity, we get the rough idea on how worse our algorithm can perform. And once we have the idea, rough idea, then we can optimize our code in different way so that it can improve in terms of time complexity, right? So the typical program takes an input and produce an output, right? Let's take a simple example here. So this is a sample program here. So each program, let's consider that this is the program, right? And each program has statement or operation, right? So it can perform some operations or statement. You have a bunch of different statements, and you need to calculate the time complexity of that algorithm or program, right? Okay, so let's try to understand what time complexity is first. Okay, so what is the time complexity? So time complexity helps estimate how algorithm runtime grows as the input size increases. In simple manner, in your program, when you have a bunch of different statements, right? And if those statements, they grow dynamically in terms of time, then we are concerned about what would be the time complexity of that program, right? In order to calculate the time complexity, so what we'll do is, let's say this is a piece of program, right? And each program has a statement, right? So you can consider each statement to run in 1 unit of time, right? And what do you want to know about time complexity? So whenever we have a statement that are inside the loops, and if the loops depend on the input, right? If loop is dependent on the input, then which means when input size increases, your loop will run n times, and then the statement within that loop will multiply n times. So in that case, it will grow linearly, right? So we'll learn about this in depth, right? So if you don't understand right now, just don't worry about that. And we also want to focus on recursion when we are calculating the time complexity. All right, so let's move on. What is a big O notation? So big O notation helps us figuring out what would be the worst time complexity of our program, right? So if we know the worst case scenario for our code, then it's easy for us to know whether this code will hit the time complexity limit, like the TLE limit, or not, right? We'll see. So big O notation tells you how much slower the piece of program gets as the input size increases, right? So for a given program, you have input, you have output, and then the program has number of statement operations, right? Let's take an example here. This is a sample program. There is one operation here, another one is here, so there are two statements here, right? So you can call each statement as one unit of time, right? When you want to calculate the time complexity. So big O is equal to functions time or space complexity. In this case, we are interested to find the time complexity of program. So let's run through some examples and see how time complexity affects per different program, right? Okay, so let's look at this example. In this one, you have a function which is taking an input number, right? And then you have one statement here, right? So this is one statement. So each statement you should assume as one, it will take like 1 unit of time, right? So if we plot the graph from 0 to n, so this is unit time and this is input size. So let's say we have one statement, right, which take 1 unit of time. So let's say there's a 1 unit of time here, right? So 0, 1, and then it goes all the way up to n, because you might have multiple statement in here, right? So in this case, you have one statement. So when this code runs, this particular statement will run only one time, right? That's why we have 1 unit of time assigned, right? And right now it's not dependent on input size. So when we plot the graph, so we get the point in here. So this is 1 unit of time, and then let's say our input size increases. So right now this n, let's say right now this n is 1, right? But if it grows linearly, let's say n would be 500 or maybe 100,000, well, we don't care. So if it's like 5, maybe here, 500 maybe here, and if it's like 100,000 maybe here, right? So in that case it's gonna grow linearly, right? So you can see, so let's say phi is here, n equal phi here, n equal 500 here, and n 10,000 or maybe 100,000, right? And in that case this line will grow linearly, like on the horizontal line, not the vertically. And vertically it stays constant, because it only performs 1 unit of operation. It doesn't matter the input grows, right? This is going to run one single time. All right, so let's move on to another one. So in this case, linear time. So this particular code here, we're interested to find out time complexity of this program. So there's one interesting thing about this program is that it has a for loop, right? And for loop has like 3 statements. So one, that's I equals 0, that's the first statement, second statement, third statement. But we don't care about this statement. All we care about the for loops are how many iteration it runs, right? So it start from 0 and array until array length. What is array length, right? So in this case, let's say n would be the array dot length, right? So the loop runs from 0 until n. So it's gonna have n iteration, right? So this loop run n times, and now that we know that each statement takes 1 unit of time, right? So consider this: there is a for loop, and within a for loop there is 1 unit of time. So if this loop runs n time, that means this will be multiplied into n unit of time, right? So if we plot a graph, so let's say both started at 0, right? So I started at 0, and in that time, in this case, this operation, this statement is not running, so at that time it's 0, right? When this loop runs, goes from 0 to n, so this loop is going from 0 to n, right? At that time, this 1 unit of time is also linearly growing in this direction, right? So you can say it's when, let's say this loop is 1, let's say n equals 1, it's somewhere here, and at that time there's a 1 unit of time, right? So in this case the graph goes like this, right? And let's say when input hits let's say maybe 10, so 10 is here somewhere, and on this side the n equals 10 somewhere here, in that case is also linearly growing like this, right? So the graph will grow like this, in the linear fashion, right? And that's the reason why this particular program has a time complexity of O of n, because in big O we're only concerned about the bigger terms, right? So 1 is less than n, right? Therefore the order, this time complexity is order of n. Okay, so let's take a look at this one. Logarithmic time, right? So we're interested to find the time complexity of this function. So what we're doing here is that this for loop, we're interested to know how many times it runs, right? So you start at 1, so let's say the 1 is somewhere here, right? And then it goes up to n, right? Goes up to n here. But look at this. Each iteration we're multiplying I equals 2, so it's jumping like 2 unit at a time, right? So what happens is, let's say when I equals 1 here, right? Then this unit of time will be somewhere here, right? So this 1 and 1, so it's gonna go like this, and then it suddenly jumps 2 unit, right? So now now n becomes 2, right? Let's say in here at that time, this is also 2, it's the same thing, so it's gonna go like this, right? But when next iteration happens, the n goes 4. However, this statement is still on number 3 somewhere here, right? And that's the reason why this graph is going in this direction, like in this direction instead of going linear, right? Because the unit time is less than the input size. This input size is jumping 2 step at a time. So if you want to calculate theoretically, so first iteration, we're performing 1 unit of time. The second iteration, we're performing 2 unit of time. But what happens when we're performing the kth iteration, right? So we use this mathematical formula 2 raised to k minus 1. For example, let's say if we're at the 4th step, so k becomes 4, 4 minus 1 is 3, 2 raised to 3 is equal to 8, right? So when n equals 8, and k is what, 4, so maybe let's say somewhere here, so we're at here 4th, but the n becomes 8 at that time, right? Which is double, right, in the size, and that's the reason why this graph goes like this. All right, and if I becomes, let's say the kth term is 2 raised to k minus 1, and we know that loop stop when I greater than n, we replace I equals 2 raised to k minus 1, and then if we take a log, so it base 2 log, right? So in that case k minus 1 less than equals log n, so k is nearly equal to log n, and that's the reason why the time complexity of this piece of program is log of n. All right, log a linear admit time, right? So we're interested to find the time complexity of this program. In this case, what we're looking here is that how many times this loop runs, right? So it's a similar, it starts at 1 and then it ends at n, right? And then it jumps 2 step at a time. So we know that whenever it jumps 2 step at a time, it's gonna put O log n iterations, right? And then there's another loop inside which is going from 0 to n, and we're only stepping one step at a time. So this is O of n iteration, right? So now and there's a 1 unit of space, there's a statement which runs on 1 unit time, so we have to multiply. So first loop n times 1, which becomes n log n, right? And that's the reason why the time complexity of this program is n log n. All right, so this program here, we're interested to find the time complexity of this. So the first loop runs from 0 until the array length, and it's incrementing in only 1 step at a time. So when it starts at 0, ends at n, so it n time, right? And there is another loop inside which is also 0 until n, which is also n times, so n into n is n square. So this statement inside, which runs you 1 unit of time, multiplied into n square. And that's the reason why the time complexity of this program in n square, we know that uh, the constant time complexity goes like this, right? But in the n square, it at some point it's gonna start to bend in the upward direction straight when you plot this on the diagram. Alright, so now we're learning about the time complexity of this piece of code here. So it starts at 0 and ends at 2 raised to n. Okay, so this is important, right? So it ends at 2 raised to n time, right? So what will be the iteration? So there are 2 raised to n iteration, right? And the 1 unit of time is multiplied into 2 raised to n iteration, and that's the reason why the time complexity of this code is order of 2 raised to n, right? And when you plot it on the graph, it's gonna go like this. And the last one, so this piece of code here, right? So there's an interesting thing about this piece of code here, that if you split this statement into two parts, right? Because there is a condition here, right? So if n less than equal 1, it performs 1 unit of time. But if it's not less than 1, then it performs n times factorial, right? Which is n minus 1. So let's say that n equals 5, right? What happens in that case, right? So n is not less than 1, right? So what happens is 5 times 4, right? Because n minus 1 is what? 4. In the second step, it's going to call the same function again and pass 4 as an input now. So 4 times 3, right? And then 3 times 2, right? And finally, when you pass 2 times 1, and then in the last step, it's going to hit this base case where n less than equals 1. In that case, it's going to return 1, right? So overall, it's going to run like this: 5 times 4 times 3 times 2 times 1, right? Which is n factorial in nature. And that's the reason why this piece of code will have a O of n factorial time. So I hope you really enjoy this video, and if you have any question, please drop in my comments, and please stay tuned. I'm going to be creating another video on space complexity separately, so stay tuned.